Okay, so this will be the second lecture we'll do on Z transforms, all coming out of chapter 5. We'll call it part 2. This particular lecture, we're going to talk a little bit more about region of convergence issues, make sure we can handle combinations of signals. That'll lead in nicely to our discussion of inverse Z transforms, which will be the main topic of this particular lecture. Inverse Z transforms, we'll find out, can be done just like the inverse Laplace transform through a partial fraction expansion in tables, but we'll also have some new methods available to us, mostly taken from power series expansion. So we'll take a look at that as well. First, though, let's do some examples that continue our previous discussions of region of convergence and make sure we can handle combinations of signals. So what I'm going to do is I'm going to go ahead and create some signals here. X1 of n, I'm going to go ahead and let be a causal exponential. I'm going to have it be a 1/2 to the n u of n type term, special case of one that we looked at last time. So we can go back and look at that lecture if you want, and we know that the transform here is just going to be z by z minus 1/2, and it has a region of convergence, right, that is norm z greater than 1/2, and we get a greater than because it was a right-sided signal. I'm going to also create another signal. I'll call it x2 of n. That one I'm going to let be a 2 to the n u of minus n minus 1. Oh, and we'll throw a minus sign out front just to make it match the table entries. This particular one is going to give me an inverse transform again from our previous lecture. x2 of z, should have labeled the first one x1. So an x2 of z being equal to, we get the same form, z over z minus now the root location is 2. And it has a region of convergence a little different. It's norm z less than 2. We get a less than because it was a left-sided signal. So we've seen this. This is all from our previous lecture. What I would like to do is look at these in combination. So I have a y of n I'm going to create as the combination, the sum of x1 of n plus x2 of n. And in this particular case, I'm summing two signals. A Z transform is a linear operator. We can see that because it's based on a summation itself. And we can hopefully just take the Z transform by summing up the two individual Z transforms we had before. We've already solved those above. And so when I get my y of z in this particular case, the first term is going to be that z by z minus 1/2, right? The second term is a z by z minus 2. And if we weren't worried about region of convergence, we could just end it right there, but the region of convergence does matter. We know the first one only converges when norm z is greater than 1/2, and the second one only converges when norm z is less than 2. For this transform to exist, we must have both regions of convergence satisfied. So that means that not only do I need the z greater than 1/2, but I also need the norm z less than 1/2. Both have to be done. We can do that both through an intersection of these two events. If I want to write that a little bit more compactly, I could write that as norm z, right, being between, sandwiched in this case, between 1/2 and 2. The way we might visualize that is to go ahead and go to our sketching idea. So I'm going to go to the z-plane, go ahead and put out my axis in there. And I am going to go ahead and throw also my unit circle for reference. So unit circle sitting in there. One of my roots was at 1/2. And we know regions of convergence can never include the value, so I'll go ahead and put my dotted circle over there. The other one was at a value of 2. Again, region of convergence would not be able to include that particular root location, so I draw a big circle, all with radius 2. If you remember the first condition here was what? It was norm z greater than 1/2. And so I'm going to be looking at all this area where we go outside of that first root, right? So I'm going to go outside of that. And that would technically go out to infinity. I'm just going to stop it here, though, for right now. And I'm going to look at the other side, which is norm z less than 2. So that's everything on the inside circle in there, something along the lines. And what we get is the place where both of these are satisfied ends up coming out to be donut shape. There is some overlap here. We can see that in the expression up above where it says the norm of z has to be between 2 and 1/2. We get definitely it's a little donut of width 1.5, if you will. There's a physical spot in the z-plane that we get convergence for both. So in this particular case, the Z transform does exist. We just need to satisfy both. The end result then is what? It's YZ equaling Z over Z minus a half plus Z over Z minus 2. And we would put the region of convergence, that combined one, of a half less than norm Z less than 2. That would be my final answer. Most of this was gotten just by using our first results, right? We had the first result that told us this piece and that part. The second result told us this piece and that part, and we just needed to combine them together. Did that through the linearity property of the Z transform. What I'm going to do next is I'm going to modify this example just a little bit. I'm going to replace the signal x1 with a new signal x3, and I'm going to let x3 also be a right-handed or a right-sided signal, but I'm going to base it on the root of 3. So I'm going to have it as b3 to the n rather than half to the n, u of n. We already know the transform of this as well. It's just another example of one of the ones that we had seen in our previous lecture. So x3 of z, right, is just going to be z by z minus 3, and it has a region of convergence in this case of norm z greater than 3, something like that. I'm going to go and create a new signal y, let's call it 2 of n, as being now x3 of n plus x2 of n. And I want to see what happens in the z transform of that. So I'm going to do this as a z transform. We should get my y2 of z in this case. Linearity should be kicking in, so I should get the result from my x3. That is z by z minus 3. And the other one is going to be what? It's a z by z minus 2. The first one had a region of convergence norm z greater than 3. The second one has a region of convergence norm z less than 2. And again, we need an intersection of those two conditions. What we notice on this is that the intersection is equal to the empty set. I can draw that out just a little bit. So we'll go ahead and put out our z-plane, and I will give myself a unit circle for reference. So there's my unit circle in there. We had our root at 2, and we have our root at 3. So I'll go ahead and put their circles on there. These are places that cannot be included for sure. So I'm going to go ahead and put 2 circles, one of radius 2, one of radius 3. That's where the regions of convergence are going to be bounding, something like that. And I know for the first signal that made up this y2, that is the signal x3, that it was looking outside, right? It was looking outside of that circle. It was a right-sided signal, and the root was at 3, so it's everything outside of this guy, something like that. And if I took a look at the other term, which was my x2 term, and that one was pointing to the inside of a circle for its region of convergence because it was a left-sided signal. That one had a region of convergence. I'm going to do this particular region of convergence in blue, was inside the circle of radius 2, something like that. Now we can definitely see, well, it looks like a pretty cool eye. There is no overlap between the green and the blue here, right? There's nowhere in the z-plane where both of these signals end up converging. So in this particular case, because I have the empty set over here, even though I get this nice expression, right, for the sum of the two pieces, that's my cap x3 of z and my cap x2 of z, I do find out that the z transform in this particular case, the z transform of y2 of n, right, does not exist. And it does not exist because there is no convergent region, because the region of convergence, right, is that empty set. So we have a little bit of a situation where both of the individual transforms end up having just a perfectly well-behaved z-transform behavior. They both have transforms that exist, but in combination they don't. And so we just got to watch that. We gotta pay attention to those sorts of things. Okay, so some observations before we move on to the inverse Z transform. We'll just take a couple quick observations. We've seen these guys before, some observations. Just want to make sure they're all in one place here. If I have a right-sided signal, right, if it's a right-sided signal, right, then the region of convergence will have a form norm z greater than some constant. I'll call it a kr, constant, corresponding to the right-sided. If it's a left-sided signal, right, left-sided signal, we know that the region of convergence, it looks like a norm z less than some constant. We'll call that k sub l. If it's a two-sided signal, so we get a two-sided signal case, two-sided signal, we know that the region of convergence will have the form, we're going to have k sub r, which is going to be less than norm z, which is going to be less than k sub l, or it might not exist. It could be a does not exist condition if there was no overlap. The final one we might talk about is a finite duration. So if I have a finite duration signal, finite duration signals, you'd never be going out to n equals plus or minus infinity. That's going to help us in our convergence. So the region of convergence is usually the entire, it's the entire z-plane. It's the entire z-plane except for norm z equaling 0 or norm z equaling infinity. And that decision depends on whether the signal has some content to the right of 0 or to the left of 0. If it has stuff to the right of 0, it can't include infinity. If it has stuff to the left of 0, it cannot include 0. We'll make more sense of that as we go later. But as a very quick example, I could look at something like this. I could take a look at a signal that was just delta. Okay, if I take the z transform of delta, so here's delta n, certainly a finite duration signal. The z transform of delta n turns out to be equal to 1, and that's for all z. There's no z in there, so there's no value z that's going to make it blow up. We can also take a look at a delta function shifted over to the right by 1, something like this. We're going to do this again here in a minute, but we'll find out that this delta of n minus 1, if we look at the z transform of that delta n minus 1, it's going to be z to the minus 1. Clearly, if I put z equals 0 in that case, it's going to go off to infinity. So this is all z except, right, norm z equaling 0. We could rewrite that just a little bit different. I could write that as a region of convergence as norm z greater than 0. It's almost everything. In the same sort of way, I could make this delta function shift off to the left just a little bit, something like that. So I'll take this particular case. This is a delta n plus 1. If I take the z transform of that delta n plus 1, right, we end up getting z. We'll prove this here in a minute. And so in the case that z was infinity, in that case, obviously it blows up because z equal infinity gives me infinity out. That's not convergent behavior. So the region of convergence here would be all z less than infinity, something like that. Finite duration signals, if they have anything to the right, that would be something like this case, then they have to not include 0. So you're going to get a region of convergence kind of like this, norm z greater than 0. If it has anything to the left of 0, then that's this case here, in which case you can't include infinity. All right, so I think we've covered all the different basic regions of convergence. We're ready to make a transition. Now we're ready to talk about this idea of inverse Laplace transforms. And so let's go ahead and get that going. We're going to be looking at the inverse Laplace, nope, not Laplace, we're in Z domain, right? Inverse Z transform, but it's just like the inverse Laplace. So inverse Z transforms, we're going to talk about here. We have a couple of options available, just like we would expect. The first one that we could talk about is the one that we used also for the Laplace transform. We can do this inverse. We can do an inverse Z by doing something like a partial fraction expansion and using tables. We'll do a quick example of that. It's very similar to what we saw for Laplace, although we might employ just a little bit different method in doing the partial fraction expansion, so we can have a nice convenient way of using our tables. So let's go ahead and try to do an example of that. I'm going to pick a signal. I'm going to call it x of z, and I'm going to go ahead and let that have the form z squared over, and I'm going to have a z minus 1, and I'm going to have a z, how about minus 2, something like that. I'm going to go ahead and give it a region of convergence. That is something like 1 less than norm z less than 2. Because I have a region of convergence that's like a donut, it has a part that's to the left of one thing and to the right of another thing, I expect that the time domain signal, the x of n, should have both right-sided and left-sided components. What I need to do is I need to take the original rational function, that's this guy, right? And I need to break it up into pieces. We've only seen a couple simple cases. We need first order Brits or first order rational functions in order to invert this guy. So partial fraction expansion can do that. I'm going to do this the incorrect way first, just to demonstrate why it's a little bit hard. I won't carry it to its conclusion, but I'll show the basic idea. Suppose I just wanted to do the regular old partial fraction expansion on this. The first thing I would notice is that that rational function is not strictly proper, right? Not strictly proper. So I can't just go and do my rational function. So it's not strictly proper in there. If that was the case, that it wasn't strictly proper, we got to get it to a strictly proper kind of guy. So we're going to have to do some sort of long division. The long division in this case would give me 1 plus something like the form of az plus b over that original denominator, z minus 1, z minus 2. This 1 that I got, so this piece right here, came out of that long division. So this one here came out of something like the long division to make this guy that was not strictly proper equal to something that is like these direct terms plus a strictly proper part. And then we would do the PFE on that strictly proper part. So if I continued this guy, I would end up getting a 1 plus, and then I'd partial fraction expand that next piece, and I'd get something over z minus 1, and I'd have something else over z minus 2. Let's call those somethings, oh, how about c and d, some other constant, something like that. You could go through your regular old partial fraction expansion methods to do that. The problem here, or the second problem, the first problem was that we had to do long division. The second problem that we have here is that if I look at this numerator, either one of these guys that comes out of this partial fraction expansion, there is no z there, right? There is no z in the numerator, no z in that numerator. And without a z in the numerator, these aren't going to match our tables exactly. If you remember, for example, if we had something like an alpha to the nu of n, what did it go to? It went to a z by z minus alpha. So we needed that z in the numerator. We don't see it here, so that kind of makes us a little stuck. That would happen every single time if you did a traditional partial fraction expansion. So we don't really like this traditional partial fraction expansion. Instead, we'd like to do something else that would help us with these two difficulties. So let me rewrite the thing we're trying to find the invert for. That's x of z. We said in this case it is going to be a z squared over, we have a z minus 1, and I have a z minus 2. And just a reminder, we had that norm z squeezed between 2 and 1 as my region of convergence going on in there. I'm going to employ what is called a modified partial fraction expansion. So that modified partial fraction expansion is what's going to hopefully help me out and save a little bit of effort here. So let's do a modified partial fraction expansion. This is also discussed in the background chapter, something you should have already taken a look at. The basic idea here is I'm going to divide both sides of the equation by z. So I'm going to be looking at, instead of just x of z, I'm going to look at x of z by z. And if I write that on the right-hand side, I'd have a z squared over, I'm dividing by z, so I'm going to get a z down there, and a z minus 1 and a z minus 2. Notice what happens here. By dividing by z, something that might not have been strictly proper before, the kinds of signals we're going to look at are either proper or strictly proper. Dividing by z is going to make those things that weren't quite strictly proper become strictly proper. This one here, if you take a look at the highest order numerator power, it's 2, and in the denominator it is 3, right? So this denominator has 3 z's in it, so it's going to be a z cubed type of term. That is strictly proper, so we could just go ahead and directly do our partial fraction expansions. Turns out in this case we also get a little bit of help because there's a cancellation that goes, and so this whole thing is left with a z over a z minus 1 and a z minus 2. Partial fraction expansions now, right, on this modified expression, x of z by z instead of just x of z by itself, should be something that's going to be over a z minus 1 and something else that's going to be over a z minus 2, something along those lines. I need to find those two coefficients up in the numerator. I can do that with my favorite method. I'm going to use the cover-up method in this particular case. If I want to find that first coefficient, the one that's in the numerator of the z minus 1 term, I go back to my original expression, this one up here, I cover up the z minus 1 and I evaluate at the root. The root was 1, so I'd have 1, that's the numerator, over 1 minus 2. That should give me a minus 1. So I'll go ahead and put that in there as my coefficient, minus 1. Same sort of an idea, cover up method for doing the other one. This one I'll be able to do just a little bit more explicitly. So if I'm gonna find the coefficient for my z minus 2 one, I cover up the z minus 2 term, right? And I'm gonna evaluate this whole thing, this whole expression at z. Well, that's not working out real well. Let's make it a little bit better here. Let's do this as we're going to evaluate at the root, z equaling 2. So if I put z equaling 2 into this expression, I'm going to have 2 over 2 minus 1, or 2 over 1. That's going to be a value of 2. So I can go ahead and put that in here as well. If you cross multiply here, you'll find out that you do get indeed the original expression. So we did do the partial fraction expansion all right here. So this whole thing was what? It's x of z by z. Not exactly what I wanted. I just want x of z. Well, now we're going to go ahead and multiply both sides by z. It seems a little weird. You divide by z first, and then you multiply by z. The divide by z helps us because it keeps us in that strictly proper place. And then the multiplying by z at the end helps us because it puts that z back in the numerator like we needed. So multiplying both sides by z, I get an x of z being equal to, in this case, I'm going to have a minus z by z minus 1, and I'm going to have a plus, right, 2, and I'm going to have z by z minus 2, something along those lines. And a reminder, we still have that same region of convergence. It's squeezed between 2 and 1, something like that. The partial fraction expansion, this modified partial fraction expansion, has helped me now. I've got the rational function that was order 2 now reduced to a sum of 2 order 1 rational functions, both of which match stuff we've already seen, so they're in our tables, and they're in the form that our tables have where there's a z in the numerator. So now I can just do a direct inverse z transform by tables. So you can see these tables in your book. You can also see them in the formula sheet for the next exam, exam number 3. We can get that x of n being equal to the first one. Because the region of convergence is to the right of that root at 1, it's going to be a right-sided signal. So I'm going to get a 1 to the n u of n. The coefficient leading it was a minus 1, so I just keep it as a minus. The second one, right, ends up having that region of convergence that is z's magnitude being less than 2, so it's to the inside of that root location, so it's a left-sided signal. I'm going to get, in that particular case, the root 2 to the n, and I have that u of minus n minus 1. There's another minus sign put in there, and then that other lead coefficient of 2 is going to give me a minus 2 in there. And this is my final expression. I ended up getting that transformed back to the time domain, and I see that that x of n is now minus 1 to the n u of n, or just minus u of n, minus 2 times 2n u to the minus n minus 1. As we had seen before, just as a real tiny final comment on here, a completely equivalent expression, right, would be x of n equals minus u of n, and I could take a minus, I could take that other 2 and put it as an n plus 1 u of minus n minus 1. Completely equivalent expression, not hard to show they're the same. They look a little different. This is just one of those quirks or I guess annoyances with Z transforms. So many different expressions in discrete time can evaluate to the same thing but look at least superficially different. So really the test you might want to do or make sure you're doing in these kind of problems is ensuring that you're plotting things out. If you're going to compare answers with a classmate or something like that, your expressions might look different but evaluate totally the same, something along those lines. Okay, so we've definitely gotten through, I think, most of the details that we need to get through about region of convergence, and we've started our ability to do inverse transforms using methods that are very similar to what we saw for Laplace transforms, namely doing a partial fraction expansion in tables. We did it just a tiny bit different. We used the modified partial fraction expansion that just really helped us match the table entries we have in this book and the ones that we've derived so far in class. What we also have is some alternate methods, and that's what I'd like to talk about next. We can now talk about the inverse Z transform. So we're going to look at the inverse Z transform by using this method, so by what we might call the power series expansion method, power series expansion method, or just by power series expansion. If you remember what a power series expansion is, a Taylor series is a form of power series expansion. It turns a function, call it x of z or whatever transform you have, it turns whatever that function is into a sum of polynomials. So if polynomials are easier to invert transform, this power series expansion is just a good tool to help us get the inverse. Turns out simple powers of z are very easy to invert transform. For us to be able to see that, I'm going to do a little bit of math. We're just going to take a look at a function. We're going to look at a function delta n minus some cap n, so a shifted delta function. If cap n were positive, it would be a delta function off to the right of the origin. If cap n were negative, it would be a delta function off to the left of the origin. And we could also take the case of cap n equaling 0, so we'd have a non-shifted delta function. If I went ahead and did the z transform of this guy, by definition, that is a summation and going from minus infinity to infinity, put in that function delta n minus cap n, and it's weighted by that z to the minus little n. In this particular case, this delta function, right, is non-zero only at a single point, and that's when n minus cap n is equal to 0, or we end up getting n equaling cap n. That's the only term out of that sum that survives. So when little n equals cap n, I'm going to get delta, which is going to be 1. 1 times then that z to the minus, but little n is cap n, so I'm going to get 1 times z to the minus cap n, or I could just write that z to the minus cap n. A shifted delta function is just a power of z. Since any discrete signal can be represented as a bunch of delta functions shifted all over, any discrete signal can have its z transform written as a series kind of expansion. Okay, so let's go ahead and show the power series expansion method in action. We'll use power series expansions to find the inverse z transform. We're going to do two cases, one which is a causal signal, one which is an anti-causal signal. So let's start at the causal signal example first. In this case, I'm going to go ahead and look at a signal x of z. So this is the transform of some signal, and I'm going to let it be z by z minus 1, where the region of convergence, right, is going to be norm z greater than 1. Because the region of convergence points outside of a circle, we know that the corresponding time domain signal is a right-sided one. The root itself is at 1, so I can do the inverse z transform just using tables. It's a single term, and I get my x of n. I know the result in this case, and it's going to be what's the root? It's 1 raised to the n. Causal, because the region of convergence points outside of the unit circle u of n. No coefficient out front, so I get 1 to the n u of n, which just simplifies to a plain old u of n. So I know what the answer is supposed to be here. I'd like to get that answer through a different method, one that doesn't require any knowledge of partial fraction expansions or tables or anything else. I would just like to be able to take that x of z, do a series expansion on it, and be able to get from that series expansion the original time domain signal. Here's the basic game on it. For a causal signal, or a causal signal component for a causal signal, I want my power series expansion to be in terms of powers of z to the minus 1. So z to the minus 1, z to the minus 2, z to the minus 3, that sort of stuff. Because z to the minus 1, z to the minus 2, z to the minus 3 correspond to shifted delta functions that are to the right of the origin, right? That's going to give us right-sided signal content. So my goal here is to take x of z and turn it into a series expansion, a sum of polynomials that are all in terms of negative powers of z. If you recall, my original function x of z was just z by z minus 1. I can get series expansions in lots of ways. I can certainly do it through something like a Taylor series expansion. In this particular case, though, I'm going to just do it straight through polynomial division. So I'm going to go ahead and take my denominator, z minus 1, and it's going to go into z. Z minus 1 goes into z 1 time. So 1 times z minus 1 is z minus 1. And to subtract those guys out, the remainder then is 1. The number of times z minus 1 goes into 1 is z to the minus 1. Z to the minus 1 times z minus 1 is a 1 minus z to the minus 1. Subtract those guys, the next remainder is z to the minus 1. Z minus 1 goes into z raised to the minus 1. Well, z to the minus 2 times. Z to the minus 2 times that z minus 1 gives me a z to the minus 1, and I can have a minus z to the minus 2. And I can continue doing this, and we see the pattern. The next term is going to be z to the minus 3, the next one's going to be z to the minus 4, and so forth. It would go on forever. You don't always see the pattern, so if it's a complicated signal, you might have to just keep doing this division. It's one of the disadvantages of this method. But for this particular one, we see the pattern quite nicely. So what does this long division do? This long division gives me an alternate way of expressing x of z, and it is a polynomial expansion. It is a power series. I get 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 plus, and so forth forever. The advantage of this particular form should be obvious now. We know what the inverse transform of 1 is. It's a delta function. Z to the minus 1 is just a delta function shifted over by 1. The next one's a delta function shifted over by 2 and by 3 and so forth. Any power of z is super easy to invert transform. So we'll go ahead and do that. My x of n, right? Just term by term here. One goes to a delta n, right? The next one goes to a delta shifted over by 1, so a delta n minus 1. The next one's a delta n minus 2, and so forth, going on forever. I could write this in a compact style, k going from 0 to infinity of delta n minus k. If I take a look at that term by term and see what I get, I have the delta n, that's this first one, right? I have a delta n minus 1, that's this guy. They're all weighted by 1. Delta n minus 2, then delta n minus 3, and delta n minus 4, and it keeps going out for infinity. There were no delta n plus something, so there was no value to be added in there. Those remain 0, so this is a function of n. This is my x of n. Clearly, we can see that this guy is equivalent to the unit step function. It's a little bit different expression. So a unit step, right, is just a bunch of shifted delta functions. They're completely equivalent expressions. We were able to get it in this particular case through my series expansion. So just a reminder, we're going to go back up for a minute. We had a expression that we were interested in, x of z equals z over z minus 1. It had a region of convergence that suggested, if we kept going, I guess, up, that it was a right-sided signal. We had previously solved this and knew that the inverse transform was a u of n. Wanted to get that u of n through a different method. We made the note that causal signals we should do as a power series expansion in terms of negative powers of z, because negative powers of z will give us deltas shifted to the right of the origin, so that gives us the right-sidedness of it. So I'm going to take that x of z. I did in this particular case a long division or a polynomial division, and I got those negative powers of z. Could have also done this through a Taylor series or some other kind of series expansion method. And then once I've got it in a power of z, this thing is just, it is trivial to inverse transform. You just get shifted deltas. And we find out that term by term, these do combine up to being exactly what we knew the answer to be, u of n. So for the next example that I'm going to do, I'm going to look at a second example, and I'm going to let it be the same. I'm going to let it be the same rational function. I'm going to call this guy y, though, and it's still going to be z over z minus 1. The only thing I'm going to do different now is instead of having z magnitude greater than 1, I'm going to have z magnitude less than 1. Again, this is an example we've seen before. We had looked at this example in an earlier lecture. So I'm going to get the inverse z transform of this as being y of n because the region of convergence points to the inside. It's a disk rather than the outside of a disk. We know it's a left-sided signal, so I'm going to get a u of minus n minus 1 type term. We still have that root at 1, so it's a 1 to the n. And because of the way the math worked out, there was also a minus sign in there. You can refer to that back lecture or the tables in the book. If I simplify that just a little bit, it's a minus u of minus n minus 1 because 1 to the n is just 1. If I plotted that guy out, it's not a terribly complicated one. This one has the first piece in there, the start of that u of minus n minus 1 is at minus 1. So it starts at minus 1, and it's going to have a height of minus 1 because of the minus sign up front. And then it's pointing off to the left. So I'm going to get a bunch of minus 1s going off and marching away out towards minus infinity. 0 at all values non-negative. So 1, 2, 3, 4, 5 going out to infinity are all values of 0. So it's just a reflected, right, negated unit step, shifted one off of the origin, something like that. The original transfer function or the original rational function was exactly what we had for x of z before. The only thing difference now is that magnitude z is less than 1, so a left-sided signal. What do we know about left-sided signals? Well, they got a bunch of delta functions, right? But all the delta functions are to the left of the origin. And because they're to the left of the origin, we know that those delta functions are going to give us positive powers of z rather than negative powers of z. So the game here for this non-causal or anti-causal signal is to do a series expansion in terms of negative powers of z. If we go back up to where we had looked before, we said a causal signal, right? We had this idea that a causal signal, you wanted the power series expansion to be in terms of negative powers of z because everything was to the right of 0. Now we're going to be looking at the case of this anti-causal signal. So I'll just write that down as a note here for this anti-causal signal, anti-causal signal. We want the power series, oh my, come on, cooperate. We want that power series expansion in terms of positive powers of z to the 1, if you will. Okay, so I still have the same rational function, right? It's z by z minus 1. I need to get a series expansion, not in terms of negative powers, but in positive powers. Well, it turns out that with a real simple strategy, we can still get what we want through long division. The basic idea here is that I'm going to reverse the order of all the terms. So this was originally written in descending powers of z. I'm going to do it just in the opposite. So z minus 1 is the same as minus 1 plus z. And I'm going to put that into the what was originally the numerator z, something along those lines. The numerator only had a single term, so reverse ordering it doesn't change anything. This is exactly the same division. I've just written z minus 1 is instead minus 1 plus z. Let's see what that minor change does for us. Minus 1 goes into z how many times? Well, it's going to go in minus z to the minus 1 times. So, whoops, not minus 1, it's minus z to the 1 times, something like that. So minus z to the 1 times minus 1 is just z. Minus z to the 1 times z is going to be minus z squared. Go ahead and subtract these guys. I'm left with z squared. How many times does minus 1 go into z squared? Well, it goes in minus z squared times. Minus z squared times minus 1 plus z is going to be a z squared minus z cubed. Subtract those out, I get a z cubed. And I can keep going on in here, but I get the pattern at this point. I'm going to have my next term be minus z cubed, and then I'm going to have minus z to the 4th, and then I'm going to have minus z to the 5th, and so forth forever. Okay? So this just reversing the order of my polynomials gave me a long division that gives me some kind of different looking terms, and it turns out to be the terms I need for the left-sided signal. So what do I get here? I get y of z, and it's going to be equal to, in this particular case, minus z, long division did this for me, minus z squared, minus z cubed, minus z to the 4th, and so forth on forever. These are, again, simple powers of z. The inverse z transform of these guys is very, very easy. Y of n is equal to then what? Z is just z to the 1. That's a delta shifted, not 1 to the right, but 1 to the left. So I'm going to have a delta n plus 1 term, and then there was a weighting factor of minus 1 up front. The next one's going to be a minus delta n plus 2. The next one's going to be a minus delta n plus 3. And I can keep going on forever. I could write this compact style. I could do this as a sum. Let's do that sum from k equaling 1 to infinity, minus sign out front, and I could have delta n plus k would be one way of doing that. If I plotted this out, if I looked at what that yn signal looks like now, delta n plus 1, right, is located at minus 1, and it's got a negative weight, so it's going to be a minus 1 at minus 1, so I have that weight of minus 1. The next one's over at minus 2, also with weight minus 1, and minus 3 with weight minus 1, and so forth, going out forever. Nothing out there that had a delta to the right of the origin, so those all remain 0 and something like that. And again, we can compare this graph to what we had before, and we see that that is equivalent to a minus u of minus n minus 1, what we had previously known as being the result. So two different examples of doing this power series expansion. If you've got a transform, y of z or x of z, some function, doesn't even have to be a rational function, and we know that the original time domain signal through its region of convergence is either right-sided or left-sided, we can power series expand it in terms of either positive powers of z for a left-sided signal or negative powers of z for a right-sided signal. We can do a power series expansion and make the inverse transform very simple. So I think that gets us through this idea of inverse z transforms. We've seen two different methods. We've done partial fraction expansions or modified partial fraction expansion in tables, and the second method is this power series expansion. Next lecture, we're going to talk about the z transform properties, very similar to Laplace transform properties, and then we'll go and continue on.